So previously we defined probability informally. Now let's take a look at a formal definition using the axioms of probability. Axiom is termed for theorems. So let's define probability of the event. Formal definition. So probability is a real valued or a set function that assigns to each event in the sample space a number that is called the probability of an event, right? So we could define probability as probability is the set function, right? Probability is a set function P that assigns to each event A, right? Let's say the event A, the function should be P, right? From where the event will be taken? From the sample space. From the sample space S. What does it assign? It assigns a number. It assigns a number called as PA. And PA, this PA is called probability of an event, right? So we have defined probability as a set function that assigns to each event in the sample space a number. It is PA and it is called the probability of an event. Now, such a function will hold some features. So characteristics, if we are talking about what is the characteristics of such a function, is the probability of an event A must be non-negative. So characteristics are, first, it is non-negative. What does it mean? The probability PA has to be greater than equal to 0. The first characteristics. So these are the condition that is needed and that should hold. The second is the probability of a sample space is 1, right? So probability of the sample space is 1. The probability of the sample space has to be equal to 1. What is the third thing? That suppose there is a mutually exclusive event, that is A1, A2, A3, an, right? All of them are mutually exclusive. We have discussed what is mutually exclusive. That means there is no intersection point between A1, A2, or each of the event. There is no intersection point. So it has to be mutually, A1, A2, and An has to be mutually exclusive. And by this we mean the AI intersection AJ is not equal to what? Any number. Or another way we call it as AI intersection AJ should be equal to a phi set, right? Should not contain any real value, right? Real value basically we are talking about. And this I shouldn't be equal to J. This is also a condition, because if the event are same, obviously there is a intersection point. So these are the three things that we will talk about, right? So the first we discussed it as a non-negative. It has to be non-negative. It has the probability of the sample space has to be equal to 1, and the events should be mutually exclusive, right? So this is the thing that we discussed. Now, if we have read De Morgan's law, that under De Morgan's law, A union B is equals to A plus B minus A intersection B, right? So in the same way, we apply probability on A union B, right? It is probability of A plus probability of B minus probability of A intersection B. We will see it. We'll see this in our later session. Uh, this property as a theorem, right? So let's use it over here. We said that each event has to be mutually exclusive, right? So if it is mutually exclusive, that means A intersection B will be equal to 0. Now the probability of any event will also be equal to 0. Hence, what will happen? The probability of A union B will be equal to probability of A plus probability of B. This we take for the two mutually exclusive event. If there is n mutually exclusive events, then the probability of A1 union, A2 union, A3 union, A4 dot union AN will be equal to probability of A1 plus probability of A2 plus probability of A3 plus dot probability of AN, right? And this is actually called as the mutually exclusive event. The probability of a finite union of event is the sum of the probability of individual events. The probability of a countably infinite union of event is also the sum of the probability of the individual event, right? So let's take an example of this, right? Let's take an example of this, and then we will discuss in our later section the theorems of the probability. So let's first write down a question that suppose there are 43 students. Suppose there are 43 students. One is a freshman, 4 is a sophomore. So let's write down 43 students are there total, where one is freshman, 4 are sophomores, 20 are juniors, and 9 seniors, and 9 are graduate students, right? So we randomly select one student from the class and we define the event, right? For that, we must define the proportion of the student. Like if the status is, we're talking about status, they are freshers, right? They are sophomores, right? They're junior, then senior, and then other grad students. So what is the count of that? It's 1, it's 4, it's 20, it's 9, and 9. So if we talk about the proportion of student, that will be 1 upon 43. It is 1 upon 43, that is equals to somewhere close to 0.02. For this again, we will do 4 upon 43, that will be 0.09. Again, this will be 0.47, this will be 0.21, and this will be also 0.21. We have defined the proportion of it. That is, so we randomly select an event. We say this for freshers, the event that fresher is selected. If we so our event is we have to select a random student from the college uh, among the random student among the 43 students right? We have to be random. So if the probability of freshers is 0. What was that number? 0.02. The probability of sophomore was equal to 0.09. The proportion, basically it's a probability. This is the percentage of students that are freshers, sophomores. So we have basically probability is a type of percentage. We have seen there in the frequency, we have seen it in the relative frequency where we decided fi upon n. So the thing that we studied earlier is now applicable over here. So this we write it, just a second. I'm defining it beforehand and I'll explain later on what is the sample space over here, right? So sophomores, and then this is junior, that is equals to 0.47, and it's a senior, that is equals to 0.29, right? Is it 21? Okay, then there is a grad student, it is 0.21, right? So we've defined this. Now the sample space is all freshers, sophomores, juniors, seniors, and grad. Usually, the relative frequency approach is to assign the probability to each event, and that we have defined, we have assigned. What is the relative frequency approach? We are talking about the relative frequency approach. What is that? Frequency approach, relative frequency approach is fi upon n, and we have the frequency. That is 1, 4, 29, 9, right? So we divide it with n and we define it as a probability. Simple. We have studied the relative frequency approach. Now let's check to make that each of these three axioms that we studied over here, this is called actually the axioms, right? What we discussed over here. These are the three axioms, characteristics, or say the axioms or theorems that are needed for what? Needed for probability to hold, right? So the first is it has to be non-negative, the probability. So from here, can we conclude that the probability of each of the event is equal to or greater than equal to 0, right? Right? So 0. If we talk it individually, you can see it's 0.02, 0.09, 0.47, 0.21, 0.21, and all of them are greater than equal to 0. The second one was what? Sample, the probability of a sample has to be equal to 1. Now, how can we calculate? The sample is equals to 43. So the probability of S will be equal to 43 upon N, and that is 43 upon 43, that is equals to 1. Now the sample space is also equals to 1, right? Let's talk about the next case. The next case is the probability of unions. So let's take probability of union if it is mutually exclusive. So let's take the probability of sophomores, no, not sophomores, but you can take it as a sophomore and juniors. Probability of sophomore union junior, right? So what we do for this, we know the probability of sophomore plus the probability of junior minus probability of sophomore intersection junior. Of course, there could be no student who is also a sophomore, also a junior. That means this event is mutually exclusive, hence it is equal to 0. Now we have to deal over here. What we have to deal? Now we have to deal in this situation, right? So the probability of sophomore union junior has to be equal to the probability of sophomore plus the probability of the junior, right? So this will be equals to, how to find the probability? We have to use the relative frequency approach. So there were 4 sophomores divided by the 43, plus there were 20 juniors divided by 43. The total is equal to 24 upon 43. Now we can put it into the decimal form. Now again we can see, if we solve this, this will come as equal to somewhere 0 0.4, 0 0.4, not 4, 0.563, something close to that, right? 0.56. And when we calculate the probability individually, that we have done it, right? This was equals to 0.09 and this was equal to 0.47. And we add up, this is equal to 0.56, right? We can use this, calculate it and check it, that whether it is equal, it's close to 0.56, not equal, but is it close to 0.56, right? So this is basically a probability. So let's recall what we studied just now is, we gave definition to the probability, that probability is a set function P that assigns to each event A, right? Probability is a set function that is assigned to each event and the sample space S, and the number is equal to the probability of the event. Then we saw the 3 axioms, or say the characteristics that are needed for a probability to hold. That is, it has to be non-negative, the sample has to be equal to 1, and it has to be mutually exclusive event. That means no 2 events have something in similar, something in common. That is, intersection has to be equal to a null set, right? Then we saw question. Now we have to define the 5 theorems, right? Theorem. So since we have seen the axioms of probability, and to derive yet more helpful probability rule, we'll work through 5 theorems in all. And in each, first stating the theorem and then proving it. Will it be okay? We will first write the theorem and then prove it. And once we have done with all the 5 theorem, we'll have a 5 method or 5 rule in our probability toolbox, which we will apply for few examples that we will see today, right? So let's talk about the first theorem, that is the probability of A is equals to 1 minus probability of A dash, right? We have to define this. Now, how to define this? We need to understand how we can just define this. So for that, we need a sample space. So let's say this is a sample space and this is A. So if this is A, what will happen? This will be A dash or A complement. Let's say A dash, right? So if we take the sample space, it is equals to, this is a sample space, that is a universal set we are talking about, A union A dash. There's no problem with that. So probability of a sample space will be equal to probability of a union A dash, and since they are disjoint, that is mutually exclusive, it will be equal to PA plus PA dash, right? And since we have read from the axioms that probability of a sample has to be equal to 1, so we can just prove it, that PA is equals to 1 minus PA dash. So this is what we had to prove, right? This is the theorem. It's a very simple theorem. We can just explain it using the Venn diagram, using this Venn diagram. It's called Venn diagram. If you are not familiar with the Venn diagram, please Google it and you will easily be able to understand what is a Venn diagram. It is basically a tool in set theory. Now, the second thing that we have to define over here is the second theorem. The second theorem says probability of a 5 will be equal to 0, right? Probability of a 5 will be equal to 0. Now, how to define it? right? So if we say A is equals to 0, let's say, sorry, not 0, but 5 set, right? What will happen? A is a 5. And since we have seen from the Venn diagram, if it is A, it will be A dash. And since it is 5, then sample will be equal to A dash, right? There's no issue about it. So for this, we can say probability of A plus probability of event A dash will be equal to the probability of S, right? So probability of a 5 will be plus the probability of A dash, right? That is equals to probability of S. And since we have seen over here, this implies probability of sample space will be equal to probability of A dash, right? So from here, we can say these two are equal, right? So probability of 5 will be equal to probability of sample space minus probability of A dash, that is equal to probability of sample space minus probability of sample, that is equals to 0. Hence from here we can say the probability of 5 is equals to 0 from the last statement from here, right? So this is what we had to prove. This is theorem number 2. You can see how easy theorems are. In probability section, we have some easy theorems, right? So let's see the third theorem. Third theorem says, and it is also very simple to explain. It's just that we need some of our tools that we use to do in that set theory. Like this says, the theorem 3 says that if event A and B are such that A is a subset of a B. So there are two events. A is a subset of a B. First condition is this. Second, that if this is true, then probability of A will always be less than equal to probability of B. That is what it wants to say, right? If this is it. How to explain it? Again, we have to build a Venn diagram. It says there is a B set and under which A comes, right? This is B and this is a subset, right? Again, we have to write it down. Like what we will write? The sample will be equal to how much? Sample will be equal to how much? It will be equal to A union. If we are talking about A union, so we are taking it as A union. And how much will the B be equal to? B will be equal to the intersection of A dash intersection B. Is there any problem in this? I'll explain you how. If this is A, whatever left is A dash. So A dash includes this portion as well as this portion, right? So if it includes this as well as this portion, that means this is A dash, and what we are talking about, we need A dash intersection B, and the B will be the common part of it. That will be this portion, right? How to find it? And this will not be equal to the sample space itself. This will be equal to probability of D. I have written it wrongly over here. This is not equals to sample space. If we have to define the sample space, we have to add one more thing, that is the union of A dash for sample space. So let's not get into that. Let's define the theorem first. This we have taken. Just a second. I have written it something wrong. This is equals to B, not that. Right. So we have to take this probability of A union A dash intersection B equals to probability of B. right? So we can just write it like probability of A plus probability of A dash intersection B, that is equals to probability of B, right? Can we write it easily? There's no issue with that. Since mutually exclusive, so mutually exclusive is the case over here, right? Now, how to define it? We take PA equals to PB minus PA dash intersection B. One thing is very certain, that this value will always be equal to greater than 0. There's no issue about this. This has to be equal to or greater than 0. And since it is equal to or greater than 0, what will happen? The probability A will be less than equal to the probability of B, right? So we have to explain this out, that why is probability of A dash intersection B is greater than 0, right? We have to define. So what is the probability of A dash intersection B? Probability of A dash intersection B also contains the part of A, some part of A, right? So we are talking about this portion. Is it okay? Now what we have to define? We must be clear this with this theorem now. So the next theorem is, if someone has any problem with this theorem, uh, please uh, go through a book named uh, this Introduction to Probability Statistics, Probability and Statistics by P.K. Rohatgi. You can just find the theorem over there. You can just go through that, right? Now, since we have defined the third theorem, let's come to the fourth theorem. What does this fourth theorem say? The fourth theorem says the probability of A will be less than equal to 1. Any event will be less than equal to 1, right? As we have seen that any event is a subset of the sample space. That is, event is the subset of the sample space, right? We have seen this. And just now we saw that just now we have discussed that if A is a subset of a B, then the probability of a is less than equal to probability of B. Simply means from here, the probability of A will be less than equal to probability of the subset. So this is theorem 3. Theorem 3. And from theorem 3, we try to prove the theorem 4. And this probability of, and since probability of the sample space is equals to 1, this implies the probability of A will be less than equal to 1, right? So we have discussed the fourth theorem also. Now there was an axiom. There was an axiom that was mutually exclusive event that we discussed over there. Let me just get into there. Where it was. Here it is. So this was a axiom, right? We used axiom when it was mutually exclusive. So for that we use this. So this De Moivre theorems. I don't remember the spelling of Moivre. So De Moivre theorem, De Moivre law. We can say this, right? So from there we will now define our fifth our fifth this theorem. And the fifth theorem says, what does our fifth theorem say? That if there are two event A and B, then probability of A union B will be equal to probability of A plus probability of B minus probability of A dash. So A intersection B. Now question arises, how to prove it, right? How to prove it? It must be lengthy. It must not be. Let's see what we need to do for this purpose. For this purpose, we take a Venn diagram, right? We make A and B, right? No issues with this. This is A, this is B. And we are clear with this term that what is this called? So this portion is called A intersection B, right? We are very clear with that. What is this called over here? This will be called as A intersection B. Now suppose we do what? We take A union B that will be taken as this entire portion, that will be A from sorry the A portion, right? And the other portion, that is this, and that will be equal to A dash intersection B. Again, A dash intersection B. The probability of A union B can be said as probability of A plus probability of A dash intersection B, right? There is no issue with that since they are mutually exclusive, right? So we defined in it in this manner. Now for this purpose, we need to draw another Venn diagram. And how to make that? Like this. There is a Venn diagram, right? We can make it this, right? So this was A intersection B. Now if we say what is B equals to, so B will be equal to how much? The one will be the A intersection B union with A dash union intersection B. A dash intersection B, right? We have defined so far this. So let's try it on the next page, or let be there on this page itself. Cannot increase. Okay. So what all things we saw? We saw uh, A union B will be equal to how much? A dash intersection B union A. From this Venn diagram, this was A, this was B, and this was A intersection B, right? This we saw. Then we write like this: A intersection B will be equal to probability of A dash intersection B plus probability of A. Now we have to take another example, this Venn diagram again. This is A, this is B. Now we have to define B. From here we have to define B. And B will be equal to how much? B will be equal to this portion plus this portion, right? So A intersection B plus what? Plus the other section. What is that? That is A dash intersection B. So now we have seen this, right? This. So from where also we can write it like this: the probability of B, that is will be equal to probability of A intersection B plus probability of A dash intersection B. Probability of A dash intersection B, right? So can we use this equation over here? So let me write down using this equation 1, what we will write it as probability of A union B as, if we have to define this portion, this will be equal to probability of what? Probability of A dash intersection B will be equal to probability of B minus probability of A intersection B. Can we write it? There's no issue. We have to just replace this over here. Use this value has to be replaced. Similarly, we replace as B, probability of B, probability of A intersection B plus probability of A. When we arrange it, this is equals to probability of A, probability of B minus probability of A intersection B. So this is our fifth theorem of probability. So far we have seen the 5 theorems of probability. Now let's do some example based on this, and from there we can just understand what is the application of this theorem, right? So let's do a question directly. The question is, a company has bid on 2 large construction projects, right? The company bids for 2 construction projects. The president of that company believes that the probability of getting the first contract, the probability, let's say, so if we have to define event, there is event A, that is first contract, right? And there is an event B, that is the second contract, right? The president of the company thinks that the probability of getting A is 0.6 and probability of getting B is 0.4, and the probability of getting both of them is 0.2. Is it clear to you? The question is, a company has bid on 2 large construction projects. The company president believes that the probability of winning the first contract is 0.6 and the probability of winning the second contract is 0.4. The probability of winning both the contracts is 0.2, right? So the first question comes over here. The first question is, what is the probability that the company wins at least one contract, right? So the question is, what is the probability that company won the first contract? Not one, but wins the first contract, right? How to define the probability for the first contract? So this will be equal to probability of A union B. So probability of getting at least one is equals to probability of A union B, right? So at least one means A. I have defined about the term union, that is A or B, and or means union, and means intersection, that I have already defined. So A or B, anything. So we already know how to solve this. So probability of A union B will be equal to probability of A plus probability of B minus probability of A intersection B, and this is quite easy. 0.6 plus 0.4 minus 0.2, that is equal to 0.8, right? We have solved the first question. Let's come to the second question. The second question says, what is the probability? If you have to note it down, please note it down. Pause and return. The probability that the company wins the first contract but not the second contract. That means we are thinking about A, A and B. We just get the first contract, not the second contract. What is this? A minus just first, not the second one. That means this thing that we can say as this is A and this is B. A minus A intersection B will be the case where you get A and not B, right? A and not B, right? And as we have seen, and means what? Intersection, and complement means not that even. A complement is not from that event A. Apart from A, anything, right? So we have discussed it earlier. Just explained you for this purpose. Now let's get back to our question. So this is the probability. So we have to find the probability of this. Probability of A minus probability of, let's write it down again. So no issue with this. This is equals to this. So the probability of A minus probability of A intersection B will be equal to probability of A intersection B dash, right? The probability of a was equals to how much? It was equal to 0.6, and the probability of a intersection B is equals to 0.2. So the probability of a intersection B dash will be equal to 0.4. The third question is, what is the probability that the company wins neither of the contract? Neither of the contract means what? Not A, not B. That means probability of A union B complement, right? How to solve this question? Since we have not studied how to solve probability of this A union B ka complement. We have not studied this. So how to solve this question, right? For this, we need to define this set. And the set will be very simple. What will be the set? The probability of sample space minus probability of A union B, right? What does it mean? Sample space, why I'm writing? Look at the Venn diagram. If this says A union B, what is left over here is the A union uh, B ka complement, and this is the sample space. The sample space minus this, the sample space is equals to 1, and the probability of A union B was equal to 0.8. This will be equal to 0.2. This is the answer, right? If we are moving to the fourth question says that the probability that the company wins exactly one contract. Exactly one contract. Fourth question is exactly one contract. How to solve this exactly one contract is? So exactly one contract means what? We have this Venn diagram. So either this, but not this, not this, right? Not this. Black one has to work. How to solve this now? So to solve this question, it is very easy. How to do it? We will just define it. What we will define? This reason, right? We have to define this reason. And how can we define this reason? We know this together is called A union B. And what we have to subtract from that? A intersection B, right? And what does it give? Gives us? That is B exactly 1. Sorry, exactly one. That means one means what? The probability of exactly one equals to probability of A union B minus probability of A intersection B. A union B is equals to 0.8 and A intersection B is equals to how much? 0.2, and this is equals to 0.6. So from this example, we have discussed almost the entire theorem. In next class, we will discuss few theorems and we will see the counting techniques. So till now we have discussed the formal definition of probability. After defining the formal definition of probability, we did some theorems, and on that theorem we did two questions. In next class, we will do 2 or 3 more examples and we will move to the counting techniques where we will be discussing about the permutation, combination, uh, the distinguishable permutations, and then based on that, there will be some examples. So in next class, we will discuss this. After that we will be left with conditional probability, event, independent event, and Bayes theorem. Right. So these are all things we have to improve. We have to understand. So in next class, we will discuss of all this. Thank you so much for today. We will discuss it in the next class.